Hi class, welcome again to another session on digital principles and system design. So we have discussed various combinational circuits and we have moved forwards to a sequential circuits. So by now I'm sure all of you are familiar with the operation of flip-flops. So let us just try and design counters using flip-flops. So before that, we are going to discuss synchronous counters today. So what is asynchronous and what is a synchronous circuit, right? So asynchronous circuit, we all know before getting into asynchronous, we all know that, flip-flops require a clock signal to perform properly. And they are a memory element, they can store the past output which can be fed as which is used as one of the inputs for the next set of incoming data. So, asynchronous circuits use just one clock pulse, like one external clock pulse is given to one particular stage, and the output of that stage is fed as a clock for the next subsequent stages. So there is definitely a propagation delay because the first circuit has to complete its operation before the next stage can start to function, can commence its operation. So that's why there is definitely a delay, and this delay keeps on adding because if there's a delay introduced by the first circuit of say 100 milliseconds, then the next circuit would it cannot compensate for that 100 millisecond loss. However, it will accumulate more delay. So ultimately, your output is lagging by a certain milliseconds. Now, this is also called as propagation delay. So, in synchronous circuits, we use a clock signal, an external clock signal that is connected to every stage of the circuit so that all stages would simultaneously receive the clock signal and therefore the propagation delay can be reduced. So this also synchronizes the operation and allows faster operation. So next things, what is counter? So a counter is just a circuit that is used to count an event. Now, why would you want a counter? A certain period of time or occasionally when you are like more into software development, you'd understand this better. But you want to monitor a particular error and see how many times that error is occurring. So you have to have a variable that actually counts. So this is a software thing. However, if you want to have a log of how many times a particular error has occurred in a given hardware, then you can use a counter circuit. So counters can be both asynchronous and synchronous in nature. And as mentioned, asynchronous counters will have a larger propagation delay because they depend on the change of state of the previous circuit or the previous stage. Synchronous circuit, on the other hand, are faster because all the flip-flops used in a synchronous circuit are triggered simultaneously. The overall propagation delay of a synchronous circuit is same as the propagation delay because of one flip-flop and the logic gate that is involved. So if you compare synchronous and asynchronous circuits, synchronous are definitely faster. So now counters can be of three types. It can either be an up counter, it can be a down counter, or it can be an up-down counter or a bidirectional counter. So up counter counts from 0 to a maximum value, down counters count from the maximum value to 0, and bidirectional can count either ways. Now, the number of flip-flops that are required in a counter equals the number of bits the counter is designed for. For example, if you want to design 3-bit counters, then you have a 3-bit counter. You need 3 flip-flops. Now, very commonly, JK flip-flops are used as counter. Having said that, it does not mean that JK is the only flip-flop that you can use for counter designing. You can do it with T flip-flop or D flip-flop as well. So, I mean, since it is popularly used, JK, I'm just going to describe the counter design using JK flip-flop, but the same principle can be applied but if you are designing one with T or D flip-flop as well. So now a 4-bit up counter, like I said, would require 4 JK flip-flops because there are 4 bits, and it requires an external clock signal that is connected to all the flip-flops, and it can count from 0000 to 1111, right? The counting sequence for a 4-bit counter is summarized in the next table. So you have an after clock pulse, that is, you have clock pulses from 1 to 17, and you have the outputs for all the 4 flip-flops. So QA, QB, QC, and QD are the outputs of the 4 flip-flops. QA being the least significant and QD being the most significant. So these are the sequences. So now if you observe, let me just take a pen out. Yeah. So now if you observe, QA changes for every clock pulse. So it is toggling. Like it is 0 for one clock pulse, 1 for the next one, and then 0 for the third, and 1 for the fourth, and so on. So it is just toggling between 0 and 1 for every clock pulse. QB, on the other hand, changes its state whenever QA is 1. So if QA is 1, then in the next clock pulse QB becomes 1. And again when QA is 1, then in the next clock pulse the QB changes its state. So QB toggles whenever QA is 1. Similarly, if you see, QC would toggle whenever both QA and QB are 1. So here you see QB and QA are 1. So in the next clock pulse you see that QC is 1. Again, when QB and QC are 1, in the next clock pulse, the QC toggles, and so on. QD toggles when all the 3 inputs like QA, QB, and QC are 1, right? So only when QA, QB, QC are 1, then the QD will change from 0 to 1, and it will remain 1 till the point when all the three outputs become 1 again, and then it becomes 0. So this is the principle that we use to design a counter. So if you see the timing diagram for a 4-bit up counter, so I have the clock pulses. So you've got 16 odd clock pulses here. So you can see that QA changes for every 2 clock pulses. Like QA is changing, and only when QA has completely changed its state, QB is changing. Again, when QA and QB both are 1, right? After both after both QA and QB are 1, then the QC state changes, and only when all the 3 are 1, QD will change. This timing diagram, however, is the ideal timing diagram indicating no propagation delay. However, like I said, your flip-flops are memory elements. They are also made up of gates, and then you'll have additional logic circuitry which is also used to construct a counter. So overall there will be a small propagation delay. It's not going to be it's not a circuit without any delay at all. There is going to be a small propagation delay. However, when you compare it with asynchronous circuit, then the propagation delay is not that significant and they are quite fast. So if you see the circuit diagram, this is what I have explained, right? So flip-flop 1 is connected in toggle mode because QA toggles for every clock pulse, and then QB toggles whenever QA is 1, QC toggles when both QA and QB are 1, and QD toggles when all the three other outputs like QA, QB, and QC are 1. So therefore, if I want to design a 4-bit counter using a JK flip-flop, I need to have 2 inputs. So this has to be the clock, and this is my input 1. So both J and K are shot together, and then they are connected together, and then it is fed with the input 1. So I get a QA output. So this is my LSB, right? And then this output is fed to the JK flip-flop. That is, if this is A, then this is the stage B, right? So output of stage A is fed as inputs to stage B. That is, both J and K are fed with whatever output Q of stage A. You can see that all these four flip-flops have individual clock signal. I mean, it's just one clock signal, but four different connections. So all of them, they're receiving the clocks at the same time. Now, like I discussed, QC is high only when both QA and QB are high. So I put an AND gate that receives inputs from both A and B, and then the output of the AND gate is fed to the J and K of the stage C. Now, QA, QB, and QC has to be high. Only then my stage 4 will be triggered. So, or only then my stage 4 will have a high output. So therefore, I just AND QA, QB, and QC using an AND gate, and then the output of the AND gate is fed to J and K of the stage. So this is how you would design a up counter. I hope you had a fruitful session learning about up counters with me. I shall see you again with more on counters. In the next video, we shall discuss down counters and bidirectional counters. Thank you very much for paying attention. I wish you all the very best. Bye bye.